everyone. Welcome back. Up next, we have the wonderful Lee Brunecki, who attendees of past PyCons may recognize. Lee is a software developer and occasional speaker from Melbourne and Adelaide. She was the conference director of PyCon AU 2020 and co-organized DjangoCon AU 2018 and 2019. She is passionate about API design, cycling, and snacks. Everyone, we will be taking questions if there is time at the end. So remember the handy little questions tab. And remember that there is a little bit of a delay from when we're talking to when you hear us. So make sure you get in your questions before Lee finishes up the end of her talk. All right. Take it away, Lee.
Thanks, Betsy. So, before we begin, I want to acknowledge that I'm presenting this from Naarm, in the heart of unceded Wurundjeri land of the Kulin Nation. I also want to highlight that there's a lot of information and a small amount of time here between my words and on-screen text, so don't worry about scribbling things down. The URL on the screen has all of the on-screen text and a list of resources. You do actually need the www at the moment, because my web server is misconfigured. I didn't have time to fix it. So this is a talk about design, and often when we think about design, we think about websites, mobile apps, book covers, and posters. We think about armchairs, shelving systems, and calculators and radios. We think of color and shape and material and texture. This is also a talk about APIs, the way that one piece of software interacts with another, whether by HTTP requests or function calls. As for color and shape and so on, they don't really apply to our APIs, which are expressed in plain text. Because of that, it's tempting to think that design doesn't really have much to offer us. But they're just the tools of design, a certain kind of design. Design is about making things for people to use. I said that APIs are for one part of a computer system to interact with another, but that's not quite true. APIs are for people to interact with software by creating more software. Dieter Rams was an influential designer, active from the 60s to 80s with Braun, who made far more than just razors back then, as well as a furniture company called Vitzo. His armchairs and calculators and such were an inspiration for hardware designers like Apple's Johnny Ive, and it's not hard to come by an analysis of his 10 principles for good design applied to websites or iPhone apps. These 10 principles are a set of short aphorisms that he wrote in the late 70s, kind of a Zen of Python, but for furniture and stuff, except, of course, design is more than just furniture and stuff. We're going to explore 5 different ideas about software and API design, and for each of them we'll look at how they relate to the 10 principles for good design, and explore what a furniture designer can teach us about APIs, something you can't touch or sit on, but which humans, our fellow developers, interact with every day. So, I've got teleprompter problems. Ram's first principle is that good design is innovative, and one of the innovations that I find really interesting is the rise of new statically typed languages. Rust, Swift, and TypeScript have type systems that are so much more expressive than, say, Java, which was easily among the most popular static type language when Python gained its popularity. They have new language features like type inference, tagged unions, and pattern matching that give you the performance and compile time bug catching that static typing has traditionally afforded, but to an even greater extent, and they give you a level of expressiveness that can, in some cases, approach languages like Python. What's interesting about these features is that they're definitely innovative, but they're nothing new. When Graydon Hoare introduced Rust to the world in 2010, literally the second sentence ever seen in public about Rust was just that, nothing new. Rust has changed a lot in the intervening 11 years, but so much of what makes Rust interesting and valuable are features that weren't invented from whole cloth. In that slide deck, Graydon goes on to say that many other older systems languages are better than newer ones, and that Rust draws from languages of the 80s and 90s. Rust documentarian Steve Klabnik elaborates that programming language research and the software industry live in 2 different worlds, and that Rust innovates by taking research from years and decades past and bringing it to a more mainstream industry context. Indeed, if you explore the community spaces where Rust or TypeScript are built, you'll see lots and lots of very researchy mathematical terms, but you'll also see lots of hard work being poured into the real value add, the real source of the innovation these languages provide. People discussing and figuring out how to make these concepts easy to understand and use, to make them accessible for people who don't have or want a deep understanding of type theory, and to communicate them so they can be best used and best taken advantage of. Now, Rams said that innovative design always develops in tandem with innovative technology, and that's what's happening here. The innovative technology was developed in all of those research languages Graydon and Steve mentioned, and Rust's innovation is largely design, language and API design, making that innovative technology useful. Rams also talks about good design being long-lasting, which is interesting, because it can feel like there's a tension between that and innovation, but they can also go hand in hand. He compares it against fashionable design, fashion and trends definitely being something that exists in the software world. Of course, the JavaScript ecosystem seems like everyone's go-to example of the hype cycle. The tools du jour in the JavaScript world do change and get replaced at an eye-watering rate, but if you step back and look at the web itself, that's a long-lasting design. The web was created a few years before I was born, and here I am. I have a career that's largely been building things for it, and I'm here talking about it. So what is it that makes the web long-lasting? I think that the main difference is that it's not a piece of software. Nobody sits down in front of their next cube and opens up World Wide Web anymore. The things that last in our industry are protocols, standards, things that multiple implementers have agreed upon. HTTP, HTML, JavaScript wouldn't have their ubiquity if they were a proprietary system. They also need to evolve. The web is kind of lucky on this one. Some time ago, when I first started in web development, Internet Explorer 6 had won the browser wars. Web standards grew stagnant, then Firefox came along. It presented a compelling alternative to web users, with features like tabs, and it let web developers do more by pushing the standards forward. It had the backing of Google. The dominance of IE6 wasn't in their interest and Chrome didn't exist yet. So Firefox not only got Google's financial support, but occasionally ad space on the most visited page on the entire web. We've been less lucky with chat. IRC has been stagnant for a while. It has everything that you need if you still live in the terminal. Meanwhile, proprietary chat platforms have been adding formatting and inline embeds and emoji reactions. It wasn't long ago, this may even still happen, I have no idea, that if you posted non-ASCII text in an IRC channel, you'd get yelled at because other people's clients didn't support Unicode and somehow that was your fault. And there's a whole other talk on the social, legal, and political factors around this topic, but free software is largely dead, and IRC is a pretty good illustration of why. The free software movement has gotten stuck navel-gazing, making deeply disturbing jokes and not getting why half the population is put off by the deeply disturbing jokes. Meanwhile, on the other side of the fence, you could exchange for a huge bucket of money in your soul a shiny box that you weren't allowed to tinker with, but at least the audio and Wi-Fi worked on day one. On that other side of the fence, we have Slack, which is largely being supplanted outside of business by Discord, and which will probably soon be replaced wholesale once more with a different walled garden. So we can't talk about software being long-lasting without acknowledging there's market forces working against that very thing, and that for many of us, our substantial paychecks come from the revenue that lock-in and disposability creates. There is kind of hope, though. My house is illuminated with LifeX bulbs, which belong to the family of Internet of Things devices, which are notorious for disposable hardware that becomes useless when its vendor goes out of business or releases a new model. And the reason I use LifeX is because they can be controlled by an open, actually documented API that doesn't involve traffic leaving my LAN. And there's a cottage industry of third-party tools that work with that API. It's hardly open standards and vendor interoperability, but it's something, right? So there's two keys here to making long-lasting technology. One is openness, interoperability, all of those sorts of things, and the other is continuing to evolve and progress and innovate. Next, I want to talk about learnability. Ram's words about how a good design makes a product understandable almost seem like they were written with code in mind, especially self-explanatory, such a common goal so frequently missed, that self-documented code is a shared running joke. To say that unironically is to tempt fate. Learnability is also a critical part of what makes an API useful. When we're writing our API, we know how it works because we're writing it, but we can't beam that knowledge into our users' heads. We also can't do that for domain knowledge around what your API does. If I'm using a library to read Excel files, it's because I don't want to deal with the intricacies of its file format. And we can't do that for the context that we work in either. Penetration tester and speaker Lily Ryan told me that to her, learnability is one of the key things that makes an API useful. APIs harm their own usefulness by being hard to navigate, offering too much or not enough, or not being set up in a way that makes intuitive sense. One place you can combat this is in documentation. In his talk, What Nobody Tells You About Documentation, Daniela Procida divides the docs you provide with your API into 4 types: tutorials, how-to guides, discussions, and reference. Tutorials are the hardest to do well, and they're the most important for your API's learnability. Daniela is a former teacher, and his talk is well worth watching the topic. Some of the critical parts are about providing a sense of achievement, being concrete, avoiding abstractions, and giving the minimum necessary explanation. We can also give our users less to learn. Back when I was doing lots of front-end work, I was installing things via NPM, referencing them via ES modules, packaging my code up with Webpack or Parcel, and doing things using the tools and conventions that are widely used in the front-end world. Then I'd use a Google library, and Google, well, they're in their own little world of front-end tooling. You can't just say import Google Maps. You have to load that script loader, tell it what to load, give it a callback to tell you when it's done, and fish the actual API out of the global scope. I can't use the import keyword with Google APIs, but I also can't use my pre-existing knowledge. I have to figure out how to get all of this weird Google stuff to work with my tools. And their docs are like this too, weird little Googleisms, unexpected details you need to know in order to make the API work, hidden in a footnote far away from the docs of what you're trying to do. Details you might just know if you worked at Google, but this is a public API that's literally made for non-Googlers. But what's really interesting is when we start talking about things like this, it often sounds like we're talking about aesthetics, which leads us to another one of RAM's principles. Code isn't particularly visual, it's just plain text, there's not a lot of flexibility or control over what it looks like. But we absolutely do have a sense of aesthetics when it comes to code. If you get the chance to go to the Powerhouse Museum in Sydney when it reopens, there's an exhibit there called Interface. It has some objects designed by Dieter Rams and Apple's Johnny Ive, and you can see the resemblance, the flow of inspiration, the shared values and priorities. You can also see a really interesting contrast. In the work of Rams and Ive, you can see this refined minimalist utilitarianism. Everything is deliberate and precise and quiet. There's lots of muted whites and greys and silvers. It's very serious, very German. And then next to that are typewriters and calculators made by Olivetti, mostly designed by Mario Bellini, and I absolutely adored them. They had lots of curved shapes, round edges, bold colours, bright yellows, glossy reds, and they were very loud and fun and very Italian. There's two different families of design here, the Germans creating a utilitarian refined tool, while the Italians sought to create an emotional reaction in the user of a calculator. And so it is with code. Across communities, we all have these different sets of shared ideas about what good code looks like. To me, good design as aesthetic in the context of APIs means writing idiomatic APIs, ones that fit in with the value system of the people using it and the code around it. And in Python, we talk about this so much, we have our own word for it, Pythonic, which includes superficial things like underscores instead of camel case, but also goes deeper. In his talk, Fabulous Blocks and Where to Hide Them, Christopher Neugebauer talks about how Python is resisted adding anonymous code blocks of the sort that Ruby has, instead preferring to introduce custom syntax for particular use cases like context managers, iterators, async, and await. And my television is about to turn itself off, so I need to find my television remote, which is a thing that I was really hoping wouldn't happen at this point. But there we go. I fixed it. These things are Pythonic, the context managers and the iterators, not my TV's energy saver timer. And so is using them. And if you have a resource that opens and closes, make it a context manager. If you have something that's conceptually an ordered collection, implement the iterator protocol so it can be looped over. Make your API fit in with the aesthetics of its surroundings, with the norms of the ecosystem it's in. And those norms, they're shortcuts too. If your users can use your API the way they're accustomed to, they don't have to remember extra details about how it works. They might even just try applying those norms to your code and go, oh, sweet, that works. And this is something that's really hard to do if you're not immersed in that ecosystem. You might end up with an API that violates your users' expectations in subtle ways, like a staircase that has fewer stairs than you're expecting. You can't do it with a book or a checklist. You really need to be part of it, interact with it, seek feedback and collaboration from others within it. So every ecosystem where your API is going to get used, there's these shared values and norms, and understanding them is key to understanding how the users of your API are going to feel when they use it. The next thing that I want to talk about is containing complexity. This is the longest section of this talk because computers are incredibly complex. And at one end, we've got very simple CPU operations that happen very quickly, and those are composed into complex tasks that are sometimes slower than we'd like. Containing all that complexity in the middle is the bulk of our job as technologists. So it can be really hard to build something that's unobtrusive, gets out of the way, and lets your users do whatever it is they set out to do. I used to do a lot of work involving content management systems and e-commerce platforms, and all of those sorts of platforms fall into two camps. Some of them set out to be simple. They follow the process of building the 10% of features that 90% of users want. They're really easy to set up, really easy to use. They're perfect so long as you're within that 90%. But if you want to make something slightly different, then you're out of luck. Others set out to do all things for all people. They've got heaps of tables and a checkbox for everything. They kind of feel enterprisey. You could do basically anything you want with them if you can figure out how. There's a Django-based CMS that's called Wagtail, which is really interesting because it's kind of the best of both worlds. And the way it achieves that is through a really interesting API. Most of the other CMSs from Django at the time, they gave you a site out of the box. They try to make it so you don't have to write any Python to get started. But Wagtail's not like that. It assumes that you know some Python and Django and made you do a little bit of coding to set up your page types. It had a few different places you could fit things, and it had a few pre-built things you could snap into those places. Or you could make your own when you needed to. The others were products with an API, but Wagtail was an API. Wagtail's API design is like Lego bricks. Instead of getting a website that you can customize, you get all the bits you need to assemble a website, with comprehensive instructions and all of the flexibility you need to change things up. The other critical thing about Wagtail is this: there's a few places you can snap in components, there's a handful of components you can snap into those places, and the interfaces of those components are expected to provide a minimal and well documented. It's pretty easy to understand how one Lego brick fits into another and how it's not supposed to, and so it is with APIs designed around this Lego brick concept. By using this snap-together architecture and also using restraint with the number of moving parts, you can make an API that enables your users to build what they want rather than getting in the way. So this Lego brick model is one approach we can take to containing the complexity of our systems. One of many ways to contain and abstract to make them fit in your brain, but is it possible to go too far? I don't have a black and white answer, but there are definitely abstractions that play a dangerous game. Rams talks about trying to manipulate the consumer, and it's easy to think of dark patterns, cookie consent pop-ups that trick you into clicking accept all, or newsletter subscription boxes that are pre-ticked. I'm going to talk about something a bit different, without that element of intent, but that can lead users down the garden path nonetheless. I'm going to talk about APIs that go further than just simplification. APIs that try to construct a facade, that try to make as if the thing they encapsulate is something it isn't. I'm going to talk about ORMs, Object Relational Mappers. When I went over RAM's principles with developer and speaker Benno Rice, as soon as I said good design is honest, they were the first thing that came to his mind. They're a popular abstraction layer for databases that come bundled with web frameworks like Django. He described their role as constructively lying to you. When you use an ORM, you interact with your data as if it's a graph of objects which are connected to each other, and you can jump between objects and walk around this graph in an ad hoc way, as if they're just there, but that's not really the case. In reality, your data is sort of structured like that, as tuples within relations in a relational database, with foreign keys sort of linking them, but that's where the similarities end. The way you query a relational database is wildly different to the API that an ORM exposes. When you query a relational database, it assembles and returns to you this rectangular structure with rows and columns. And unless you're using SQLite, you're usually talking to your database over the network. This is all happening in a different process, probably on a different machine. ORMs have to do a lot behind the scenes. When you make a query, they translate it into SQL, get that rectangular result, split it out, make some objects, and link them together, constructing this graph that they present to you as they go. They're laying down track ahead of the train like Gromit, trying to make it seem as though it was there all along. And they work. For simple cases at low load, everything is fine. But that constructive lie is at the root of a lot of sharp corners. More complex queries often end up being harder to write in an ORM than they are in SQL. You need to understand the SQL that you want to generate, how that works, and what the performance characteristics of that are, and you need to understand enough of the innards of the ORM to make it produce roughly the SQL you want. The ORM lets you do complex queries, but it's rare that you can do them entirely at the ORM's abstraction level without thinking about the SQL underneath. Then, once you've sent off your query, there's that illusion of the data being right there, which is a source of even more sharp corners. This is a trap that's so common, so easy to fall into, that it has its own name, the N+1 problem. What you can't see, what the ORM is lying to you about, is that author isn't really there yet. When you access the author attribute, the ORM goes off and finds an entirely new request, doing a whole bunch of network I/O, constructs an author object out of the response, pretends it was there all along. That's inside the loop. You're hitting the network every iteration. That's going to slow things down. The solution is to tell the ORM in advance what you're going to do with it. So you have this API that's lying to you to try and make it simpler, but in order to get good performance, you have to break the illusion. You have to know about the lie, know about the circumstances when it's lying, and code around it. This same feature is one of those caused headaches down the road for the people building the library as well. Resident Django mad scientist Andrew Godwin has spent the last few years trying to make Django async, and with Python's async I/O syntax, you can only yield to the event loop to wait on I/O with the await keyword. So this model of the ORM might hit the network at surprising time through attribute access doesn't really work with async. And in his talk at last year's PyConline, Andrew revealed that his solution is that you just have to use select related. The code with the N+1 error, that just doesn't work in async mode. So that tells us that when we simplify, we need to tread with caution. Are we simplifying or constructing a facade? How complex is it? How surprising is its behavior? Now, to be clear, Django's ORM is very, very good. It's technically impressive and still has a well thought out API. It's just that to implement things the way that Django has decided to do requires doing this deal with the devil, constructing this facade. And to its credit, Django does let you pop the hood. It's pretty easy to provide custom SQL and still get all the other niceties. And that's a good lesson to take away too. It may be constructing a facade, but at least it's thorough about it. How's that for a segue? The most thoroughly design software is like the most thoroughly designed physical object, with polish and finesse through every path you might take as a user, not just the most common. Less thorough designs might just focus on the most common use cases or expected outcomes. And similarly, it's easy to end up designing an API with a lovely thought-through happy path, but not even think about errors, letting them bubble through to your users, straight from the library you're depending on, or the runtime, or the framework, and the documentation, not even a mention. The design of the error cases is left to chance, and that means that the inner complexity of your API leaks out to users. A thorough API will not only handle errors well, but for each of the kinds of errors that can happen, the documentation will tell you what circumstances they might happen in and guide you towards how to handle them. A thorough API, when you hit those errors, will also have good error messages. Rust is really good at this. When you hit a compile time error in Rust, the compiler has this lovely, pretty clear error message. It tells you where it found the error, what it was expecting, what it got instead. It gives you a hint for what it thinks you might have done wrong. There's lots of information here, sometimes enough to fix the error straight up, and other times enough to get you started figuring it out. React has an interesting approach to this too. Production builds of React try to minimize code size, because when you use React on your website, every visitor has to download all of React. So they don't have big, long, lovely error messages, they have error codes. And this is one of the cases where it still makes sense to use error codes in this day and age, other than, say, microcontrollers. But in React, the error code gets embedded into a URL, and you get a clickable link in the debug console, and when you visit that link, that's where you'll get all of the detail. You get a nice error message, you get a description of what the error means, some common causes for that error, and advice on where to look, and links to documentation to learn more. And this is a really neat approach that I'd really love to see more of, both in web frontends and in the terminal. Now, as for errors in Python, yesterday's education track had a great talk by Andre Roberget that's all about Python stack traces, which touches on the things I've talked about here, as well as the effects on learnability. Now, the other case where it really shows that an API is well thought through, where it shows that an API has polished out the corner cases, is when that API enables you to polish out the corner cases in your own work. Accessibility features tend to be less well-trodden paths. Collectively, a decent amount of us probably use one or the other, but individually, they're relatively rarely used. And more importantly, rarely used by developers, unfortunately. And if your API can make it easier for your users to build accessible software, more of them will actually do that, which is a win for your users and theirs. Complexity is often inevitable in computing, and the best we can do is contain and compartmentalize it. Having unobtrusive abstractions like the Lego bricks model, while being cautious around building facades that aren't honest, and thoroughly designing our edge cases and error paths can help contain that complexity and rein it in. I'm ahead of time, I've earned a sip of water. So through all of that, we've talked about three key themes: protocols and evolution, learnability, containing complexity. And across those themes, we've touched on 8 of RAM's 10 principles. I'm going to close out by discussing one more, but first I want to briefly talk about the one that I've left out. Good design is environmentally friendly. Our industry has an impact on the environment, and with the climate crisis upon us, it's a topic that's as important as ever. But unfortunately, I really couldn't find a way to do it justice in this talk, so instead I'm going to recommend Miriam McLeod's talk from 2019. It's called Environment Variables, it's linked in the resources, and it's a really well put together overview of the topic that I can't recommend enough. Rams closes his 10 principles with this, and it's where I'm going to end this talk as well, because I think it's possibly the most important. Good design is as little design as possible. Definitely not as little work to design, but an end result that's minimal and focused. This is something that translates really well to API design, and I'm pleased that it's last because it translates to something that to me is really quite important. Something I think about a lot when I'm designing APIs. And the way that I think about it is what I call cognitive overhead. Nothing is infinite. The machines that run our software have limited resources. So to varying degrees, we optimize how much of those resources we use. We might try to write code that runs faster, uses less RAM, writes less out to disk, or communicates less over the network, or uses less battery. And we use a bunch of different tricks for that. If we can avoid doing something entirely, we will. We look for opportunities to use the same resource for more than one thing if we can. We might defer things to run later. Maybe there's a component that might not be needed at all. Or maybe there's 20 components we'll need to use eventually, but not at the same time. Or we might pre-compute things we might know or think we might need later if we've got more free resources earlier on. Nothing is infinite, and that applies to developers too. There's a limited amount of things we can remember. And there's an even more limited amount of ideas and concepts and facts that we can keep in our working memory at any given time. There's a limited number of hours in the day, a limited amount of time before we have to have made progress towards whatever we're building. It might seem kind of trite to say the human brain is just like a computer, but when you start to think about API design in this way, you notice that optimizing your API design for cognitive overhead is pretty similar to optimizing your code to run faster. The solutions often sound similar in an abstract sense, and you end up using the same sort of creative problem solving you might use to optimize something else. You might try to use fewer concepts so that your users don't have to swap things in and out of their working memory. You might design your API to use certain concepts in certain places, so they only have to hold things in their working memory when they're working in those parts of the system. You might reuse concepts or patterns from the tools you're building on top of, like languages and frameworks. I didn't talk about a thing that I'm saying in my script I'm going to talk about, so I'll skip that. And all of the ideas we've talked about feed into this. Protocols, evolution, and long-lasting technology create a shared language that aids learnability, creates that shared aesthetic that acts as a learning tool. Learnability and understandability go hand in hand with this principle, and containing complexity, doing that well, being unobtrusive, honest, and thorough so that the complexity doesn't leak out, those are key components of how we achieve minimal cognitive overhead, how we make our designs as little design as possible. It feels weird talking about APIs as being for people, and I think that's because we have this divide in how we think about people. We have users, commoners, who know nothing and need help understanding computing. Then we have developers, the smarter, superior class, who know everything already. It feels weird because of contempt culture, because of the superiority complex we have as developers. And so we think we don't need design. We think about the people that use our APIs and we think they're developers, they know computers, they don't need help, they already know this. Or perhaps we don't think about the people that use our APIs. Perhaps we think about code as something that we're building for the computer. The thing is, unless you're directly fiddling with binaries in a hex editor, there's layers of abstraction between what you write and what the computer runs. Computers are dumb machines that are good at doing simple things very fast. They don't need abstractions. The abstractions are for humans. The code we write is mostly for humans. My name's Lee Brunecki. We've only got a couple of minutes, but I may be able to take one or two questions if I remember to step out of my graphic. I'm not going to take comments, even if they are disguised as questions. If you comments, feedback, want to say hi, I'll be in Venulus. There's contact details on the screen as well. And I also want to thank Lily Ryan and Benno Rice for helping me tease some of my ideas past my writer's block and suggesting some directions I wouldn't have thought of on my own. So, if we have some questions, I would love to hear them.
Hi, okay, so we have some questions. Half of them are about your presenting setup, so while they're very good questions and I want to know the answers, I'm gonna leave those aside. While everybody is just like absorbing all of that and coming up with their questions, and you have a moment to breathe, Lee. Sorry. I just want to take a moment for a round of applause for the stenographer. Well done. Whichever of the stenographers is doing the live captioning for this one, you're a champion. Great work. Okay. So we have some questions and we have 1 minute.
Ooh, lightning round.
So how do you manage tensions between the different principles? How do you prioritize one thing over some other?
It depends. I mean, it's one of those things where you sort of got to think about, I guess, it depends on the specifics of what trade-offs you're making, who your audience is and stuff like that. I think it's probably one of those situations where the better you have an understanding of who's going to be using your APIs, the more you'll be able to make those trade-offs. But yeah, I don't think there's really a one-size-fits-all answer to that one.
All right. And we are at time, so there is another excellent question there that I will copy across to the chat, if that's all right with you, Lee.
Sounds good.
So we will move this over to the text chat, the Curly Boy Theater chat, in the channels part of the menu on the left. I have no idea if I'm gesturing at the left or not of your Venulus. Thank you again, Lee. And we now have a little bit of a break. We'll be back here in 15 minutes at noon for our next talk.
All right. Thanks, everyone. Bye.